Chapter 9, Circles. Today we're going to cover Section 9.1, Basic Terms. Your class opener. 1, draw a circle, and 2, describe as many things about the circle as you can. Our objectives for today. Define a circle, a sphere, and terms related to them. Recognize inscribed polygons and circumscribed circles. First, for some terminology. A circle. Many people know what a circle looks like, but what's the definition for a circle? Well, a circle is the set of points in a plane that are all equidistant from a given point. So if I start with this given point, here's a circle. It's the set of points that are all the same distance away from it. The next term we have is radius. Well, a radius is a segment that connects the center point to a point on the circle. So here's going to be my radius. The third one, a chord. A chord is just a segment where the endpoints are on the circle itself. So if I draw a segment where the endpoints are on the circle, I get something that looks sort of like that, where the endpoint could be anywhere else as long as it's on the circle. So there's going to be a chord. A diameter. A diameter is just a chord that passes through the center. So if I pick one that looks like this. So if I pick a chord, goes one endpoint on the circle, passes through the center of the circle, and the other endpoint is over here. That's going to be a diameter. Number 5 is secant. A secant is just a line that contains a chord. So if you think of a chord as being a segment where the endpoints are in the circle, imagine if you just extended it farther, you end up with a secant. And the last one, 6, a tangent. A tangent is a line that intersects the circle in only one spot. So if I sort of draw one similar to the secant, instead of hitting the circle in 2 spots, it hits the circle in only one place, and then this would be described as a tangent. And the one spot right where it hits, if I could imagine the 2 of them hitting right here, would be called the point of tangency. Some basic terms here. A sphere is the set of all points in 3-dimensional space that are all the same distance away from a given point. The radius is still going to be pretty much the same thing. So if you imagine where the center of the sphere is, the radius is the segment that connects from the center to any location on the sphere. A chord is still a segment that intersects the sphere in 2 places, so the endpoints are someplace on the sphere. A diameter is a chord that goes through the center, so the endpoints are somewhere on the sphere going through the center. Secant is still going to be a chord or a line that contains a chord, so it's going to intersect the sphere twice and keep on going. And a tangent is still going to be a line that intersects the sphere in only one place. Congruent circles and spheres are circles and spheres with congruent radii. We knew before that congruent meant same size and shape. So if I have 2 circles that have the same exact radius, then they're going to be congruent circles because they're the same exact size. And then the same thing with a sphere. If you have a second sphere that has the same exact radius as the first one, they're going to be congruent to one another. Concentric circles. Circles that lie in the same plane and have the same center. So the most important part is they're sharing the same center and they're all in the same plane. I always think of it as like rings for a bullseye. The one thing that's sort of deceptive about this picture is it looks like the distance between each of these rings is the same. That doesn't have to be the case for concentric circles. So I could have another circle that would still be concentric if it had the same exact center, and even if it was, and I know it looks like it's off a little bit here. So even if I had this circle right here, it's still concentric to the other ones. Even though the spacing isn't the same, it has the same center. And the same thing for spheres. So spheres that have the same center are concentric spheres. Inscribed polygon. A polygon is inscribed in a circle if each vertex of the polygon lies on the circle. So if I look at all the segments that make up the polygon, all the vertices happen to be on the circle itself. And then a circumscribed circle, a circle is circumscribed about a polygon if each vertex of the polygon lies on the circle. So the polygon is inscribed, it's on the inside, and the circle is circumscribed, it's going around the outside. Number 3, part A, draw a right triangle inscribed in a circle. So the first thing I want to do is draw myself a circle. So I do that, and if you're freehanding it, just do the best that you can. So here's going to be my circle. Drawing a right triangle. So I need to get some segments in here. So I'm going to start by drawing a segment over on this left side. And I know that I'm going to try to draw a right triangle, so I'm going to try to make a 90-degree angle, and then connecting up the other side should look something like that. So here's my right triangle inscribed in a circle. Part B, what do you know about the midpoint of the hypotenuse? Well, if I found the midpoint of the hypotenuse, the interesting fact that we know about the midpoint of the hypotenuse is it's the same distance to each vertex. So even if I measure that distance to the vertex over here, all of these distances are exactly the same. Part C, where's the center of the circle? Well, if that midpoint is the same distance to all of these vertices, and all these vertices happen to lie on the circle, it must mean that this midpoint right here of the hypotenuse is the center of the circle. And then part D, if the legs of a right triangle are 6 and 8, find the radius of the circle. So if I look at my circle that I have up here, if my legs were 6 and 8, and it's asking me to find the radius, well, if I do Pythagorean theorem, I can find the entire hypotenuse, and if I cut it in half, I'd have the radius of the circle. So let's go through 6 squared plus 8 squared equals x squared. 36 plus 64 equals x squared. 100 equals x squared. We take the square root of each side. So I know that the entire hypotenuse is 10, which means the diameter is 10, and the radius would be half of that. And I get that the radius is 5. For each exercise, draw a circle and inscribe the polygon in the circle. So nothing special, there's no particular exact shape, just get this done. So here is my circle, and I need to draw a rectangle. Well, I know for drawing a rectangle that I need to make 90-degree angles and opposite sides have to be parallel. So I'm just going to start by drawing in a segment like this. I know that I need to make a 90-degree angle over here. And it's going to be a 90-degree angle down at the bottom. And it should be a 90-degree angle over here. And it got off by a little bit. And this side looks like maybe it should be right there. So there's my rectangle drawn inside of my circle, trying to make these all 90-degree angles. Number 8, an obtuse triangle. So I'm going to start by giving myself a circle again. Well, I know if I'm making an obtuse triangle, I need to make an angle that's bigger than 90 degrees. So how do I make an angle bigger than 90? So I'm just going to start with a segment. Now if I was trying to make a 90-degree angle, I would make an angle that looks sort of like this. So bigger than 90 means it's going to have to come over this way somehow. And now just connect the other two pieces together. So here's my obtuse triangle. For each exercise, draw a circle O with radius 12, then draw radii segment OA and segment OB to form an angle with the measure named. Find AB. So I'm going to start by drawing myself a circle, and I'm actually going to start by just drawing in where the center of my circle is going to go. And they want me to draw in radii OA and OB so that it forms a 180-degree angle. Well, if I'm going to make a 180-degree angle, and here's OA, OB is going to have to go in the opposite direction. That way it forms a straight angle. The problem wanted me to make a circle that had a radius of 12. And they want me to find AB. Well, since it was a straight angle, I just can add 12, and 12 is 24. Number 15. Drawing the same thing, but now I need to form a 120-degree angle. So I'm going to start by giving myself a center again. Make a circle. And I'm going to start by giving me a generic starting point. Let's say here's going to be OA. And I'm going to approximate a 120-degree angle. Well, I know how big a 90-degree angle is, so I imagine going about another 30 degrees, making a 120-degree angle. So if here's OA, here's OB, this is 120 degrees, and I'm supposed to find AB. So I'm now supposed to come in here and find out what's the length of that piece. Well, I know a couple of things. The first thing I know is the radius is 12. And the second thing I sort of notice is if I take a 120-degree angle and I cut it in half, I end up getting a triangle like this that actually ends up being, this is going to be a 60-degree angle, which means out here is a 30-degree angle. So now I have a 30, 60, 90 triangle, and they want me to find the distance of AB. So the first thing I'm going to do is, I know if OA is 12, if I travel to this piece right here, it's going to be half of that, it's going to be 6. And then if I go from there to just this one piece on this triangle, it's going to be 6 square roots of 3. Well, the same thing's going to happen in this other triangle, and I'm going to get 6 square roots of 3. So the entire length from A to B is 12 square roots of 3. Either add the two together or just take one of the 6 square roots of 3 and multiply it by 2. And your closure. The part of this lesson I understood the best is what because of what.